Today we have discussed most important theorem, that is, if the function has derivative at a point C, then the function has the continuous at the point C. Okay, if we have the derivative of the function at point C, then the function is continuous. But if the converse of this statement is not true, because f is not a sufficient condition for existence of derivative. Now let us prove it. We have to find out f is continuous at C, so we take it that type of thing, fx minus fc, which is equals to fx minus fc, taking on denominator and numerator x minus c, because we know that it is given that f has a derivative at C is in I. So since f dash c exists, then this implies that taking limit both sides, this gives limit extending to C fx minus fc upon x minus c, limit extending to C x minus c. If x tending to C, then this becomes 0 and this becomes f dash c, right? Because f dash c exists, so f dash c into 0, this becomes 0. This implies that limit x tending to C, fx minus fc is equals to 0. So this shows that limit extending to C, fx equals to fc. So this implies that f is a continuous at C, right? But if we then take converse of this statement, that if the function is continuous, then this implies that it is differentiable or not. So it is not differentiable. Continuity of the function does not imply that the existence of derivative, as I say earlier, right? That is fx equals to mod of x. Let us take example, fx equals to mod of x for x is in R, and then the derivative of the function is mod of x upon x, which is it is, if x is greater than to 0, then the derivative exists for 1, the limit of this is 1, and if x is less than to 0, then it is minus of 1. So there exist right hand and left hand limits are both are differed, so therefore the function is not derivable at 0. So hence this implies this continuity is not a sufficient condition for the derivative to exist at C.